Have you ever found yourself puzzled by how to compute a homography matrix between two cameras? It can be a tricky topic, but don't worry. Today, we're going to break it down step by step. I totally understand your confusion. Many people struggle with the concept of homography, especially when it comes to understanding the relationship between rotation, translation, and camera intrinsics. You're definitely not alone in this. Let's dive into the specific question at hand. One user recently asked, how can I compute the homography matrix if I already know the rotation and translation between two cameras, including the camera intrinsics? This is a great question, and one that many in the field encounter. To understand this, we need to clarify what homography is. Essentially, it describes the transformation between two planes in space. When you have rotation and translation, you can indeed compute the homography matrix, but it requires a bit of math. Stick around, because by the end of this video, you'll not only understand how to compute the homography matrix, but you'll also be able to apply it to real-world scenarios. Trust me, you won't want to miss this. To compute the homography matrix, given the rotation and translation between two cameras, the user should start by understanding the relationship between the camera intrinsics and the rotation and translation vectors. Next, the user needs to incorporate the translation vector into the homography calculation. This can be done by modifying the rotation matrix to account for translation. Now, if the user wants to warp an image using the homography matrix, they should ensure that the points being transformed are in the same plane. If not, they may need to adjust their approach. Finally, the user should test the homography matrix by applying it to a sample image. This will help verify that the transformation behaves as expected. Fun fact: did you know that the concept of homography is used in various fields, from computer vision to robotics? It's fascinating how math can bridge the gap between different disciplines. Now let's look at the answers provided by other users. This user points out that if there is a non-zero translation and the image contains more than just a plane, the images cannot be related by a homography. They explain that some points visible in one image may be occluded in the other. They also mention that if the image includes a plane and you estimate a homography using only points on that plane, the homography will accurately transform points on the plane, but will misrepresent other points. Here's a pro tip: always visualize the transformation. Drawing out the rotation and translation can help solidify your understanding of how the homography matrix works. And there you have it. You now have the tools to compute the homography matrix given rotation and translation. Remember, practice makes perfect. If you found this video helpful, please subscribe for more insights and tips.